Okay, welcome to our last example video for projectile motion. What I'm going to do here is I'm going to basically just walk through one calculation while narrating what I'm doing, and then the second one I'm going to be quiet and just calculate it very quickly. Okay, so what I'd like for you to do is to follow along with me for the first set of calculations, and then pause it, try the second one on your own, and see how close you can get. Normally in class, I would run this as an in-class example for everyone to try calculating this, but now we can actually kind of take a little bit more time to do it on your own at your own pace. So the example that we're looking at is a question of which object will go farther. We have an object that gets launched from the ground with an initial speed of 20 meters per second at an angle of 70 degrees from the horizontal, and an object launched from the ground, again with an initial speed of 20 meters per second, but at an angle of 20 degrees from the horizontal. So we're going to be calculating two different distances here. And before we do this, you should probably take a second to think, which do you think will go farther? The one that's launched at 70 degrees and goes very high into the air, or the one that's launched at 20 degrees and moves very fast in the x direction? We're going to split our paper in two, and we're going to work over here. Let's do the 70-degree angle over here and the 20-degree angle over here. So the very first thing I'm going to do is I'm just going to make a sketch. Let's do the 70 first. You guys can do the 20 on your own later. I'm going to make a very quick sketch of the 70-degree launch. Okay, so it's 20 meters per second at an angle of 70 degrees. Now, I'm going to need to split up my variables into x and y variables. All right, so that means I'm going to put my x's over here. I'm going to need to know dx. I need to possibly know Vix, Vfx, and I'm getting this just from the tables that you've seen on the front of this sheet and on the back of the other sheet, in case you're wondering where I'm getting these from, okay? It's always the same ones, and Ax. In the y direction, I'm going to need to know maybe dy max, Viy, Vy top, Vfy, and AY. And under other, I'm going to list time and the angle. Okay? Well, I'm already given the angle. The angle is 70 degrees. And my most important things that I need to know, oh, I didn't even set the direction as positive. There we go. Let's make up the positive direction. And to the right as well. So the acceleration in the y direction is therefore negative 9.81 meters per second squared. Negative because I just directed that the direction up was going to be positive. I could have said down was going to be positive, and then this would be positive. It's completely up to you. The x direction acceleration is 0 meters per second squared. Now, I have to split this initial velocity up and figure out the components of the initial velocity in the x and y directions. If you remember from the reference tables, the initial velocity in the x direction, or the x component of a vector, is given by the magnitude of the original vector multiplied by the cosine of the angle. So my initial velocity in the x direction is simply going to be 20 meters per second times the cosine of 70 degrees. Cosine of 70 times 20 is 6.84. Oh, this is really crowded. I'm sorry. I'm just going to write this over here. 6.84 meters per second. And because there's no acceleration, I know that that's the final velocity as well. 6.84 meters per second. I don't know the distance. That's what I'm looking for. Okay? I guess I don't know the time right now. I don't know how high it's going to go. I can find the initial velocity in the y direction, though. That's simply going to be the initial velocity multiplied by the sine of theta, which is 70 degrees. So, because remember, to find a y component, it's whatever the magnitude of the vector is multiplied by the sine of the angle. So in this case, it's going to be 70 sine times 20. 20 meters per second times the sine of 70 degrees equals 18.79 meters per second. There we go. Okay, sorry, it's a little squished. The velocity at the top in the y direction is 0, because at the peak there is no velocity in the y direction, and Vfy would be negative 18.79 meters per second. That's the velocity when it comes back down. okay, right before it hits the ground, not when it's on the ground. Don't use when it's on the ground because then it doesn't have this acceleration anymore. Soon as it starts to impact the ground, the whole problem changes. We don't care about that. We care about the velocities and the distances and everything else right before an object gets out of projectile motion, okay? So, I've got pretty much everything that I could want. I might as well just try solving for the distance in the x direction right now. I know that the acceleration is 0, all right? So that means I'm not going to use this equation or this equation because that'll just end up getting me Vf equals Vi, which is true in the x direction, but not useful. So I'm going to use this equation. dx equals Vix plus 1/2 ax t squared. And a note about subscripts. Don't think that I and x here are variables. They are subscripts. They are just descriptions of what velocity I'm talking about. This tells me I'm talking about the initial velocity in the x direction. If I hadn't put these, I might get confused and think I was talking about some other direction. I might have been talking about the y direction, or I might have been talking about a final velocity. And then I wouldn't have plugged everything in right, and I could have gotten the wrong answer. Anyways, dx equals Vixt plus 1/2 ax t squared. There's no acceleration in the x direction, so that's 0. So I'm down to this. dx equals Vix. I know that that's 6.84 meters per second times the time. Well, that's unfortunate because I don't know what the time is. But that doesn't mean that this has been a waste of time. There's a pun. This doesn't mean that this has been a wasted opportunity. It means if I can figure out the time, then I can plug the time into this equation and I can find my distance. Now, how am I going to find the time? In all the other problems, we've said that time is almost always found using the y variables. Okay? So I'm going to use my y variables. I'm specifically going to use the fiat equation. Vfy equals Viy plus ay times t. Since I like to cancel things out if there's 0, I'm going to treat the final velocity in the y direction as if it's this final velocity at the very top, okay? I know that that's 0. Cross that off, that's 0. The initial velocity in the y direction is 18.79 meters per second. That's positive because we're launching this thing up, plus negative 9.81 meters per second squared times time. I subtract the 18.79 over to the other side and divide by negative 9.81. So that's negative 18.79 divided by negative 9.81. The time for this object to go from its launch to its peak is 1.915 seconds. Remember, because that's only the time to go from launch to peak, to get the total time, because it's still moving forward for the total amount of time, I need to multiply this by 2. And I get 3.83 seconds is the total time. Now I can take that total time, because time doesn't have an x direction or y direction. Time is a scalar. It's just a number. Has no direction to it. I can take this time and I can plug it back in over here. And if I do that, then I end up with this. 6.84 times, meters per second, times 3.83 seconds. And we get 26.2 meters. Now let's remember that number. What I'm going to do now is be quiet, and I'm going to do exactly my problem-solving process for solving for the distance if we launch this at an angle of 20 degrees. Notice that the speed is the same, okay? So we're just comparing the launch angles right now. So I'll be quiet. You can follow along with my work. Feel free to pause the video and try this on your own. If you get stuck or confused, just start the video and you can see where you've gotten to and where you would pick up, or where I pick up your work from. going to write them down here. Okay, so I want to point out a few things about this. Number one, in both examples, notice that I didn't even need to find the maximum height in order to do this problem. I could have found the maximum height, it wouldn't have been a bad thing, but it wasn't necessary for me to do so. Sometimes there's numbers that it's not necessary for you to find. It doesn't matter if you don't know something, you can solve it or you can get around it by using other equations. So we didn't need to know the maximum height. If we had found it, great, but it didn't necessarily help us, okay? It didn't hurt us, but it didn't hurt us. Wait, hold on, I got confused. We don't need to know it, okay? Sorry, that's where I was getting at. Secondly, notice that I solved for the time in a slightly different way than I did over here. Here, I said my final velocity was the velocity at the peak, which is 0, and I multiplied by 2 to get the total time. Here, I remembered that the final velocity is just the negative of the initial velocity in the y direction. So I put a negative here, and I solved for the total time right off the bat. I plugged this in, and you'll notice that I got something slightly under 26.2 that I got over here. I got 26.1, and sometimes people look at that and they're like, oh, so this one went farther. That's just a rounding error. These are so close that this can't be coincidence. As a matter of fact, if you go back and don't round anything, then you'll get the exact same answers, okay? So it turns out that it doesn't matter which one you want to go for, it doesn't matter which one you pick, they go the exact same amount of distance. And this is true if you have a very special set of circumstances. So, two objects that get launched with the same initial velocity at the same time from the same place will land in the same spot if the angles that they are launched from are complementary. What does complementary mean? You learned this back in math class. When two angles add up to when two angles add up to 90 degrees, they are said to be complementary to one another. If you have this situation and the angles are complementary, then the object will travel the same amount of distance. Why is that? Again, it's a trade-off. I kind of explained this at the beginning. The object that gets launched at a high, steep angle will spend a lot of time in the air, okay? Over double the amount of time this one spent in the air. But notice the x velocity is much smaller, okay? The velocity in the x direction. The one that gets launched at a lower angle has a much higher velocity in the x direction, but not as much time in the air, so it's a trade-off. The two factors that influence how far something will go are its velocity in the x direction and how much time it spends in the air, okay? It just so happens that if you launch at complementary angles, the distances work out to be exactly the same. One other thing I want to point out is that so basically, if I were to keep increasing, let's say I increase this by 1 degree, I decrease this by 1 degree, so that they're still complementary, okay? I could keep doing that all the way until I met in the middle. What's the middle of 20 and 70? It would be 45 degrees. It turns out that if you want to launch something for the farthest possible distance, 45 degrees is the best angle to launch from. 45 degrees ensures that you're going to have the biggest possible horizontal distance covered. Okay? That's not to say that 45 degrees is always the best angle to launch at. If you want something to go the highest in the air, then obviously you launch at 90 degrees. If you want something to spend a lot of time in the air, obviously you launch at 90 degrees. But if you want the maximum horizontal distance for a given initial velocity, you launch your object at 45 degrees. Okay? End of story. That is it for projectile motion. There are tons and tons and tons of ways that projectile motion can get asked about. On your projectile motion homework, you're going to see as many of those as I could find. Okay? So when you get this homework, when you start doing it, realize that there are some questions where you're going to have to find the horizontal distance traveled, but there's a lot of other questions that stop well short of that. There's a lot of questions that ask, find the maximum height, or find the time that the object is in the air for. There's even questions that just say, find the x component of the initial velocity. So you have to read very carefully and know what the question is asking for. In a lot of cases, it's good to write out your variables. You might not always have to do so, especially if it's a conceptual question, but if it's a longer question that requires a lot of you, then yeah, it's a good idea to write out your variables. Again, I'm going to stop it here. We'll spend some time talking about projectile motion in class. Other than that, I think we're pretty much good, so I will talk to you later on. All right, well, next time you see me on video, we'll be talking about the beginning of our forces unit. Finally be done with kinematics. We'll finally be talking about forces. Very excited. All right, see you later.